Hi everybody, we're David England, Gordon Mancuso, and Peter Oyen, and this is our presentation for Lab 3. First, we'll take a look at parts 1 through 3 of the lab, which are creating our K-maps, doing our K-map reduction, and doing a Boolean reduction or Boolean minimization to verify that result from our K-map. We'll start with the left front output, and we can see here that we only have one prime implicant with 4 minterms, so this leads to a fairly simple reduction. We can see by writing out these minterms that the values L and C stay the same for each minterm, so that means our function is true when L and C are both true. Next, for our Boolean minimization, we can see for each pair, the first pair and the second pair of terms, that we can take out the S's, the S and the S naught from each of those pair of terms using the distributive theorem. And since S naught plus or S is 1, that just leaves us with L naught RC and LRC. And we can repeat the same process for those two terms, taking out our R naught and R, and that leaves us with LC, verifying our result. Next, we'll take a look at our output for the left back. And we can see here that this time we have 3 prime implicants. First one here, number 2, and number 3. And that leaves us with no extra ones. So we've got all our prime implicants that we need. And here are the minterms here. So here we've got 3 different equations for each of our prime implicants, which means we repeat the thought process that we did for the left front implicant. We just do it 3 times. So the first one we get LC, the second one we get S not L, and for the third one we get S and R. And next we'll verify that with a Boolean reduction or Boolean minimization. So here we can see that there's quite a few more minterms for the left back than there were for left front, but the process is essentially the same. In order to use the commutative and distributive theorems to do this minimization, we've got to add a couple duplicates in here, which have been highlighted for you. And once we do that, we can use the commutative theorem to order those in an order that allow us to use the distributive theorem to take out the non-like terms from each pair. And so we've done that here. That'll reduce our equation to this one here, and then we can do that one more time to take out the non-like terms from each of those pairs, and we end up with the same equation we got from our K-map reduction. And here is the K-map reduction and the Boolean reduction for right front. It was essentially the same as the left front, but with different minterms. So we end up with R and C, making the function true. And for the right back, as with the left back, we've got 3 different prime implicants, but we end up using the same process to reduce this, and our answer is here below for the Boolean reduction.
For part 4 of the lab, we're asked to take the Boolean equations from part 3 and create our circuit in LogiSim. We'll notice that left front and left back have common components CL, right front and right back have common components RC. This allows us to create a more simplified circuit.
With the circuit complete, we need to compare the circuit output to the original truth table. To do this, we can activate each combination of inputs and record the corresponding output. We could also use the Analyze Circuit feature found in LogiSim. Analyze Circuit is found under Project. We then select Table on the Combinational Analysis window.
Next, we can compare the original truth table to the LogiSim output. In looking at the left front, left back, right front, right back, we can see that the output matches.
In part 5 of the lab, we explored the use of a ROM as a lookup table. ROM stands for read-only memory. There are many uses for a ROM, and one of them is to use it as a lookup table. The inputs of the ROM point to memory locations or addresses inside of the ROM. The addresses are specified by the inputs. Here's an example of a 256 by 4 ROM. Because it has 8 binary inputs, it can hold up to 256 addresses. The key step to implementing a ROM as a truth table is to specify the output as a hexadecimal number. Here's the truth table from this lab. Because this table has 4 binary outputs, we use a single hexadecimal number to represent each output state. For example, this output here corresponds to the hexadecimal number C. We similarly fill in the rest of the outputs. This is the completed circuit in Logisim. We can modify our inputs and therefore affect the output. The ROM can be edited in one of two ways. We can edit it directly using the poke tool like this. A more powerful option is to open the hex editor, which allows fast keyboard navigation between the values. To conclude, we have learned that using gates directly to implement a circuit can be a complex process. Even after significant minimization of the Boolean problem, the gated circuit in this lab still has many parts. In contrast, the ROM lookup table yields a clean, simple, and easy to understand circuit design. The process to create a ROM lookup table is very straightforward, with no minimization necessary. A possible drawback to the ROM implementation is that the ROM basically is a black box, and depending on the technology being used, it may not be an appropriate solution. Thank you for your attention.